I wanted to make sure that you had some pieces of information before we talk about the ideal gas law, because it might make a little bit more sense. First of all, when we say ideal gases, we are talking about standard conditions or close to standard conditions. So remember the signifier STP, and that means 0 degrees Celsius and 1 atmosphere. Atmospheres being pressure, 0 degrees Celsius being temperature. It also, there's several assumptions that go along with ideal gases. One of them is that because gases, particles are so far apart from each other, so you think of a tiny little pin top atom or molecule and a tiny little pin top atom, you know, close to it, you're not going to have any mutual attractions. So the assumption is that there are no mutual attractions between particles of a gas, partially because the distance they're from each other, the size of them, the volume that they take up, etc. So also, gases have no fixed position. If you remember from earlier discussions you might have had about a gas position, not positions, we say that gases are moving very quickly. They don't really stay in one position all the time, and that's just kind of the nature of a gas. We also say that the particles themselves have no volume. Volume, remember, is taking up space. So we say they don't have any volume, even though they technically would take up space, but it's so small of an amount compared to the volume that the gas takes up that we say they have no volume. And so we call them point masses. This is just a term that's used to signify the little tiny mass that a gas would take up. So when we use the word ideal, how is that different from real gases? So this only becomes significant distinction at small volumes, because then gases are going to have volume. Gas particles, their volume becomes important. Because they would start to attract to each other, right? So when we're doing the gas laws, we are really considering the ideal situation. When you start talking about things outside the ideal, that doesn't obey this law, and so you have to use different laws, and those are beyond the scope of this class. We're going to focus on the ideal gas law. So here are the conditions that would be outside our scope. Highly compressed state, which means small volume and high pressure. So on the flip side of this sheet is a text reading you're welcome to read. There's also a section in your book titled The Ideal Gas Law. You can read that to get more information or to see how it's explained in a different manner. So that's really just the background, and now we can talk about the ideal gas law. If I'm going to pause for a second. If you have questions about this, you can go ahead and unmute yourself and ask the question.
So the no mutual attraction, that doesn't include gravity, right?
Right. It would just be attractions like a positive, negative, electrostatic attraction, that kind of attraction.
Okay.
Any other questions? Okay, let's go to the other sheet, the ideal gas law, this one. And we'll talk through this. Now this one is on, this is from section 13.5 in your book, which starts on page 415. So when you're reading and taking notes, this suffices for your notes. So you won't turn these into me since we're doing them together, and you will not need to take extra notes for yourself because basically I'm telling you what it says. Okay. So remember Avogadro's formula, gas law, was volume over moles. And the combined gas law was vice president over treasurer, right? Mm-hmm. Those are the variables. Not really vice president or treasurer, that's just how we remember it, VP over T. If you combine these into one equation, you get VP over NT. So if we set it up like we did our other laws, we would have this scenario. And from that, we build up to the actual formula for the ideal gas law. This side of the equation, we instead call it R, or the ideal gas constant. This is dependent on standard units. And the standard units would be, let's just list them, would be 1 mole. What would be standard volume for 1 mole? You can unmute yourself and answer. 1 mole would be what volume? Come
Liter.
on.
22.4 liters.
Yes, 22.4 liters. All right, mute yourselves again. Okay, temperature, 0 degrees Celsius, 1 atmosphere. Now, the one thing that you need to make sure that you always do is convert the temperature into Kelvin. You have to have the Kelvin temperature in gas laws, not Celsius. That's always important. So if I take these units and I set them up in my equation, I'll just rewrite it here. And I just set it up so I have 22.4 liters, that's my volume. I have 1 atmosphere. I have 1 mole, and I have 273 degrees Kelvin. When I calculate this, and you can calculate it if you have your calculator, you'll find that the number you get is 0.082, and I want you to go 1 more digit and do a 1. So 0.0821. Notice, look at your units. None of the units cancel out. So you have a complex unit, liter, atmosphere, per Kelvin, mole. So this is the R value that you must memorize. Now I'm going to do one more because you need to understand that I can change my R value based on pressure units. But to simplify our lives, we're just going to use atmospheres always for pressure. And then you don't have to worry about what R value to use. Okay. So if the pressure is in torr or millimeters of mercury, again, we would simply put in our units, but the one that would change would be our pressure units. What is 1 atmosphere in terms of torr and millimeters of mercury?
760 torr or millimeters of mercury.
Correct. So we'll use torr because it's easier to write. So if I do that, then I have an R value in terms of torr or millimeters of mercury. So when I use it, I would have to make sure my pressure is in torr or millimeters of mercury. So you can calculate any R value based on this equation for any of the pressures that we used, as long as you use the standard pressure unit. So for this one, if you've had time to calculate, you would have 62.4 millimeters of mercury or torr. Oh, sorry. Let me do this in the same order. That would be helpful. So it'd be liter, atmosphere.
No, liter torr.
Oops, I did it again. Mess up. Liter torr per Kelvin mole is a unit. So that's also one that you can use if your pressure is in torr. But again, if you just convert all your pressures to atmosphere, then you only need to know one R value, which is up here. Okay, so the ideal gas law is affectionately called the Pivnert equation, because if we just rearrange everything, we get Pivnert, PV equals nRT. That's a rearrangement of this equation up here that we were working with earlier. So make yourself a note down here. Most gases obey the ideal gas law, or this equation, at pressures of approximately 1 atmosphere or lower, when the temperature is 0 degrees and higher. So basically, for most situations that I'm going to give you that deal with moles or mass, this is the equation that you're going to use, the Pivnert equation. Okay? Any questions on that page? I'll pause before I flip to the next.
0 degrees Celsius or Kelvin on that last note there, or Fahrenheit.
0 degrees, I'm sorry, yes, 0 degrees Celsius, thank you. Anybody else? Okay, let's flip to the next page, and there's a couple problems we can try here. Okay. So the question says, when a rigid hollow sphere containing 600 liters of helium gas, so here's our volume, is heated from 300 Kelvin to 600 Kelvin. So here we have 2 temperatures, but really what we want to know is the change in temperature. So 300 to 600 would be a change of 300 Kelvin. That would be our temperature that we're going to use for this. The pressure of the gas increases to 18 atmospheres. So there's my pressure. It asks for how many moles. How many moles of helium does the sphere contain? So that would be N. The missing piece is our R value in order for us to use the PV equals nRT, but our pressure is in atmospheres, so we can just use 0.0821 liter atmosphere per Kelvin mole. Okay, so PV equals nRT is the equation. So we're just going to substitute our values. 18, and I'm going to drop off units. 680 is the volume in liters. Important to point out here, volume has to be in liters. Because notice in the R value, we have liters. So we have to make sure our volume is in liters. N, we're looking for the R value 0.0821. And T has to be in Kelvin. It's 300 K. So N, when you calculate, it's just algebra solving for the N value. Hopefully you get 400. Let's put dots after these so we can have 3 significant figures. So I would have gotten 500. Helium.
Dot.
And that's significant figures right there.
That's what I got.
Actually, no, I did that wrong. It should be 498 moles of helium.
I'm sorry for anyone who's doing this in pen.
Sorry, so sorry. I was doing it in pen too. See, I had to scribble on my page.
Well, you can just erase your pen.
Yeah.
See?
Okay, let's do a going further kind of question. So let's say that the question then added, what mass of gas is in the sphere? How would I do that? What mass of gas?
So now we must hearken, brethren, back to stoichiometry.
That is right. We have to harken back to the days of mole conversions. So we have 498 moles of helium. Helium is 2 moles. Oops, I'm sorry. 2 grams. I am not hearkening very well. To 1 mole. Where would I get that information?
The periodic table.
Periodic.
That's right, periodic table. So we solve 498 times 2, it's about 1,000.
996.
996 grams of helium. So sometimes the questions, especially on your problem set, they're towards the end of it, I believe, you're going to have to calculate mass. So you cannot stop with PV equals nRT. You have to go one more step further and calculate the mass. This question here, we're not going to worry about, okay? Because it's annoying.
Lung capacity.
Yeah.
Now, before I scratch all that out, we're sure we're not doing anything in there?
Yes, Noah, scratch
right.
it out. You have full permission to scribble. Okay, so now flip over to the problem set number 2 that I gave you. And if you don't have it with you, I'll